In this section, we're going to look at titrations. And titrations can be very complicated mathematically because they involve a combination of math and logic. And unfortunately, they do take practice. So in this section, we're going to go through a few examples, which isn't going to be quick. But after we go through several examples, hopefully you'll have a better understanding of how a titration is working. So before we do that, I want to remind generally what a titration is, and you may have done one of these before in a lab. So here we have a base in what is called a burette, and a burette is just a graduated tube. So when we let the base come out into the acid, which is down here, we can measure the amount of base that we used. Here in the flask, we have an acid. And we often add an indicator to that acid. And when the indicator, in this case phenolphthalein, turns pink, then we know that the moles of acid and the moles of base are equal. And if we know the concentration of base, we can find the concentration of acid. Or if we know the grams of acid, we can find the concentration of base. Or if we know the concentration of acid, we can find the concentration of base. So it allows us to calculate something we don't know based on something that we do know. So that's what a titration is very useful for. But it turns out that we can also monitor titrations by pH. And in a few minutes, what I'm going to look at is some calculations to find some points on a titration curve. But realistically, if one were doing this, one would do it experimentally where we add, okay, it's not shown here, but we add some amount of base to this acid, and the pH is, well, actually, it looks like it's going down. So now it's in a base, and the acid is being added, and the pH decreases, and we measure the volume of acid added versus the pH. And sometimes we also will put an indicator in here. In this case, the methyl red indicator is in here, sorry, methyl orange indicator. And basically, this is being monitored by an indicator for a visual, but it's also being monitored by a pH meter, so we know the specific pH and the amount of acid added. So there's two essential ways that we can do this with strong acids and strong bases. And we're going to basically break this section up into three areas, with the first two being more about titrations, and then the last one a calculation where you can find molar mass. In the first area, what we're going to look at is the titrations of strong acids and strong bases. And we have two examples here. In this case, okay, we have NaOH being added to an acid. So we start with the pH meter in an acid, and we can tell that because look, the pH is around 1, so it must be an acidic solution. So this is a strong acid, such as HCl. We then add NaOH, and what happens to the pH? The pH starts to go up. But then it starts to go up really, really fast around the equivalence point. And the equivalence point is at a pH of 7, because if we're titrating HCl and NaOH, we're going to make NaCl in water, or salt water, which is neutral, which has an equivalence point of 7. Then the pH continues to increase as we add NaOH. It increases very quickly for a while, and then it starts to level off, okay? The reason that we have the pH increasing fairly slowly here is because it's still mostly acid in this region. Even though we are adding NaOH, we're not substantially changing the concentration of the acid. And remember that a pH scale is a log-based scale, so it's powers of 10. When we get close to the equivalence point, the pH starts to change rapidly. And then at the other end, we're basically just adding base to base, and the pH just changes relatively slowly. We can have exactly the opposite of this. In this case, we have NaOH in the flask, which we can tell because the pH is quite high, so we know we have a base in the flask. Then we add HCl, and the pH drops. But in both cases, the equivalence point is at 7. What you're going to find if we use a weak acid and a strong base, or a weak base and a strong acid, is the equivalence points are different depending on which direction you do the titration. And we'll talk about that in a minute. Well, not in a minute, but a little bit later in this lecture. In this case, what we see is it doesn't matter which way we go, the equivalence points are the same. And the reason for that is if this is HCl and NaOH, you have NaCl and water in solution, and therefore it is neutral, and the equivalence point is at 7, whichever direction that you go. So what we want to do is we want to find sum of points on this titration curve. Now, to make a curve that looks like this, okay, you might need 10 or 15 points, and it will take all day to get 10 or 15 points. And as I mentioned before, this is often determined experimentally, where you can use a drop counter or you can do it manually, where you add a milliliter or whatever of NaOH at a time, and you record the pH on a pH meter, and then you make this graph in, Excel or whatever the case may be. Here, we're just going to find 5 points because we don't want to be doing math for the whole day. So basically, we're going to find 5 points on our titration curve, and then we're going to, sketch in the rest of it as best I can using, the computer. So it says, what is the pH of a solution before the titration begins? Before we do that, let me tell you what we're doing. We're taking 52 milliliters of 0.1 molar HCl, and we're titrating it with 0.135 molar NaOH. And we want to find the titration curve, or several points on the titration curve, as follows, okay? So first thing I notice here is that we have the NaOH in the burette, and we have the HCl in the flask. Since we have the HCl in the flask, it means we're going to start at a low pH because it's going to be acid pH. We are then going to take NaOH from the burette, and we are going to add it to that HCl in order to and measure how the pH changes. Now again, here we're doing calculations, not measurements, and so it's a little bit different. It says, what is the pH of the solution before the titration begins? So when 0 NaOH is added, what is the pH? So we have 0 and the pH. How many milliliters of NaOH must be added to reach the equivalence point? Okay, so we don't know what the equivalence point is, but we do know the pH will be 7. Why? Because we have strong acid and strong base. What is the pH of the solution at the equivalence point? Well, that we already know. The pH of the solution at the equivalence point will be 0 because it will be NaCl and H2O. What is the pH of the solution when 14 milliliters of NaOH is added? I don't know, but we can calculate with 14 milliliters of NaOH what is the pH of the solution. And what is the pH of the solution when 44 milliliters of NaOH is added? So we have 44 milliliters here, and we want to find the pH of the solution. So this is not a straightforward thing to do, but we can go ahead and do these 5 calculations, and basically we will get some idea of what the titration curve will look like. But again, you'd have to do 15-ish points if you wanted to get a more sketched out view, but in the interest of not doing math all day, we're not going to do that. All right, so it says if 52 milliliters of 0.1 molar HCl is titrated with 0.135 molar NaOH, answer the following questions. And these are the same questions. What is the pH of the solution before the titration begins? So we need to find the pH of the solution before the titration begins. Well, before the titration begins, we have 52 milliliters of 0.1 molar HCl. It turns out that it doesn't matter how much HCl we have to answer this particular question. What matters here is the concentration of HCl. Remember that HCl, aqueous, reacts with water, liquid, to form H3O plus aqueous plus Cl minus aqueous. All right, so H goes with H2O to form H3O plus, and we have Cl minus left over. Remember that because HCl is a strong acid, this is not a reversible reaction. This reaction goes to completion. Said another way, the concentration of HCl equals the concentration of H3O plus equals 0.100 molar. Well, now we can find the pH, because pH equals the negative log of the H3O plus concentration, which equals the negative log of 0.1100, which equals 1.000 technically. Okay, so the pH of the initial solution is 1.00. The next question says, how many milliliters of NaOH must be added to reach the equivalence point? So here we have HCl reacting with NaOH to form NaCl and water. And we already talked about when we form just NaCl and water, the pH would be 7. So we know the pH at the equivalence point, which is actually the next question. But we want to know how many milliliters of NaOH it'll take to get here, because remember, on our graph, we have volume of NaOH added and the pH. Well, the pH is 7.00, but what is the volume added? So that's kind of the question for this one. Well, how are we going to do this? Actually, this is a stoichiometry problem that was presented in General Chemistry 1. In this case, what are we starting with here? We're starting with liters of HCl. 52 milliliters, we're going to have to convert that to liters. We want to convert that to moles of HCl, then to moles of NaOH, and finally we want to take those moles of NaOH and convert it to liters of NaOH, because it asks us how many milliliters of NaOH must be added. So this is a stoichiometry problem. So we need to take this number of milliliters and convert it to liters, divide by 1,000, which is 0.0520 liters of HCl times. We need to convert liters to moles. To convert liters to moles, we use molarity. And 0.1 molar means there's 0.1 moles of HCl in 1 liter. So therefore, we put 1 liter of HCl on the bottom and 0.100 moles of HCl on the top. Once we have moles of HCl, we can convert it to moles of NaOH using a balanced chemical equation. So 1 mole of HCl on the bottom and 1 mole of NaOH on the top. Finally, we want to convert it to liters of NaOH. In order to find liters of NaOH, we need to use the molarity here. But we're going to use it upside down compared to how we use this one. So in this case, it's 0.135 molar, which means there are 0.135 moles of NaOH, which I want on the bottom so that it'll cancel out, per 1 liter of NaOH. And when I do all that math, I find that it takes 0.0385 liters of NaOH to do this titration. It asked me for how many milliliters, so I need to multiply that by 1,000, which is 38.5 milliliters in order to do this titration. So here's the deal. When I have added to this solution 0 milliliters of NaOH, the pH is 1. When I've added 38.5 milliliters of NaOH, the pH is 7. So we found 2 points on that titration curve that we talked about previously. So now we need to find the other points on that curve. What is the pH of the solution when 14 milliliters of NaOH is added? Let me pull that down. What is the pH of the solution when 14 milliliters of NaOH is added? What we need to remember is that we have 52 milliliters of 0.100 molar HCl, and we have 0.135 molar NaOH. All right, so this information is in the previous question, which I probably should have re-put here, but I didn't. I have seen a question just like this when I was helping somebody prepare for the MCAT exam. So this is, a question, if you're interested in that kind of thing, that could be asked of you. So there's lots of ways to do this, but what I'm going to do is I'm going to find moles of NaOH and I'm going to find moles of HCl. So I need moles of HCl and I need moles of NaOH. Now, I can be sure that the pH is going to be less than 7. Why? Because we just calculated 2 seconds ago that it takes, what was it? 38.5 milliliters of NaOH to make the pH be 7. So I know I'm going to be less than 7, but let's see exactly what it is. Well, to find moles of HCl, I need to use this, all right? So I'm going to take 0.052, whoops, let me try again, 0.0520 liters of HCl times, just like we did before, we're going to put 1 liter of HCl on the bottom and 0.100 moles of HCl on the top. And when I do all that math, I find that there is 0.00520 moles of HCl in this solution. I now need to repeat the same thing for NaOH. Well, I added 14 milliliters of 0.135 molar. So I can't use milliliters, I have to use liters. So 0.0140 liters of NaOH, just divide by 1,000, times, in this case, 1 liter of NaOH contains 0.135 moles of NaOH. And when I do that math, I find that there's 0.00189 moles of NaOH in this solution. So I have this many moles of NaOH and this many moles of HCl. Not surprisingly, we are going to have more HCl than NaOH. But remember that HCl aqueous reacts with NaOH aqueous to form NaCl aqueous plus H2O liquid. So for every mole of this I started with that reacted with a mole of this, I'm going to turn that into NaCl. Said another way, I'm going to have less HCl than I started with because some of it reacted with the NaOH. Specifically, to calculate the current HCl, I'm going to take the 520 moles of HCl and subtract the 0.00189 moles of NaOH. And remember that I'm subtracting them 1 to 1 because the stoichiometry here is 1 to 1. You'd never see an example like this where it wasn't, I don't think, but it is 1 to 1. And it's certainly fair game. I personally wouldn't give that. All right, so we subtract these two numbers and we find that there are 0.00331 moles of HCl in the solution after we add the NaOH. Again, it is not surprising that there is more HCl than NaOH because we haven't reached the equivalence point yet. But remember, in order to find the concentration of HCl, I need to consider the volume in liters. I'm going exactly where I went before, which concentration of HCl equals concentration of H3O plus. And then I can find the pH once I have the concentration of H3O plus. So I need to take this and I need to divide by the total volume. Well, that is 52 milliliters plus 14 milliliters, which is 66 milliliters, but I need to convert that to liters, so I need to divide by 0.0660 liters. And when I do that, I find that this is 0.0502 molar HCl. Well, this is also the concentration of H3O plus because they're equal because HCl is a strong acid. So pH equals negative log of H3O plus. So the pH equals the negative log of 0.0502. The pH equals 1.30. So notice, when we've added 14 milliliters of HCl, we change the pH from 1 when we added no milliliters to 1.3 after 14 milliliters have been added. It changes very slowly at the beginning because the solution is still predominantly acid until we get close to the equivalence point, and that's when the pH shoots right up. Not an easy problem, but we were able eventually to figure out the pH of the solution. Now it says, what is the pH of the solution when 44 milliliters of NaOH has been added? Well, it turns out that because of the way the HCl works, the number of moles of HCl are constant. So the moles of HCl in the initial solution is still 0.00520 moles. Why? Because the moles of HCl are based on the 52 milliliters of 0.1 molar HCl. They have nothing to do with the milliliters of NaOH that are added. Note that this is the initial number of moles, right? It's going to be different after the reaction. But in this case, we actually went past the equivalence point, because remember the equivalence point was 38.5 milliliters. So in this case, we're actually going to have excess NaOH. So we need to figure out how many moles of NaOH that we have in this solution. So to find the moles of NaOH, I'm going to take the volume in liters, 0.0440 liters times the 1 liter on the bottom and the molarity number of moles on the top, which is 0.135 moles of NaOH. And when I do all that math, I find that there are 0.00594 moles of NaOH. Because we're doing the exact same problem, every mole of NaOH is going to react with a mole of HCl, assuming there's enough NaOH. In this case, we actually have more moles of NaOH than we do of HCl, which is not surprising because we had 44 milliliters, which is greater than the volume of the equivalence point. So in order to find the moles of NaOH currently, we need to take the 0.00594 moles of NaOH, and we need to subtract out the 0.00520 moles of HCl. So basically, we're finding the moles of NaOH that are left over. And when we do that math, we find that there is 0.00074 moles of NaOH in the solution after the 44 milliliters of NaOH is added, and most of it reacts with the HCl. Now we can find the concentration of OH minus by simply dividing this by the total volume. So we had 52 milliliters of the HCl, and we have 44 milliliters of the NaOH. 52 plus 44 is 96 milliliters, so I need to divide by 0.0960 liters. And we find that we have 0.0077 molar NaOH. Remember that concentration NaOH is exactly equal to the concentration of OH minus, because every NaOH gives us an OH minus in solution. So what I can find here is the pOH. The pOH equals the negative log of the concentration of OH minus. This is the concentration of OH minus. So the pOH equals the negative log of 0.0077 molar. Then, when we do that math, we find that the pOH equals 2.11. And if you remember from the previous chapter, pH equals 14 minus the pOH. So pH equals 14 minus 2.11, which is 11.89. Now, if we switch back to the graph here, we find that what is the pH of the solution before the titration begins? When 0 NaOH is added, it's 1. So the pH is 1, and we can plot that on our graph. What is the pH at the equivalence point? Well, the pH at the equivalence point is 7, and how many milliliters did that take? 38.5. So 38.5, we get a pH of 7. What is the pH of the solution when 14 milliliters of NaOH is added? So at 14 milliliters, we found that the pH was 1.3, as shown here. And what is the pH of the solution when 44 milliliters of NaOH is added? It's 11.89, which is up here. So now we're sketching in the titration curve, and it's not perfect because I had to draw it with, kind of by hand. So this is the points on the titration curve. Important take-home messages here, okay? The pH starts off low. Why does the pH start off low? Because we started with just acid in our flask. At the equivalence point, the pH is 7. Okay, so that's the equivalence point because you have NaCl and water in this case because we added HCl and NaOH. The other thing is the pH increases slowly for quite a long time until we get near the equivalence point, and then the pH goes up really fast. Once we get past the equivalence point, it levels off and then it continues to rise very slowly. So this is the strong acid titrated with a strong base. If we titrated a strong base with a strong acid, we would get the same thing. It would start off high, then it would drop, and then it would, level off at a low pH as we added more and more acid. So it's just kind of the opposite. In the next case, which unfortunately the math is actually even worse than in this case, what we're going to look at is a weak acid and weak base type of titrations. So we have two different examples here, okay? We are going to focus on a weak base and a strong acid, but we could also do a weak acid and a strong base. So if we look here, we have a weak base and a strong acid. And there's a few things to notice here. The first thing is we get this initial dip in the pH. So we're starting off with a weak base, so the pH starts off relatively high, but we get this quick dip. And the reason we get that quick dip is because we start to make a buffer. Because as we start to add acid to this, we start to get weak base and its conjugate acid. Said another way, we get a buffer. So we quickly drop into the buffering region and we see this little dip, if you will. We then have a buffer all throughout here. It turns out, for mathematical reasons, if we go to a volume that's half of the equivalence point, the pH is equal to the pKa of the acid, of the weak base, sorry. And the reason for that is Henderson-Hasselbalch equation. When the concentration of base over the concentration of acid are equal, pH equals pKa. Next thing to notice, if we notice when we're titrating a weak base, the equivalence point, the pH is less than 7. Why? Because at the equivalence point, what's in solution? Conjugate acid. The solution is completely filled with conjugate acid, and the conjugate acid is acidic, and therefore the pH is less than 7. Finally, when we come down here, we start to reach the similar thing that we did with the strong acid and a strong base, because now we're just adding acid to acid. Okay? Now, it is possible sometimes that you could get, in a diprotic or triprotic acid, you could get multiple of these different equivalence points. And sometimes even, you can have bases that are conjugate acids technically. So, this is not a hard and fast rule, but this is similar to what we're going to see on our titration curve here. Let's look at the opposite case, and we're not going to build one that looks like this. Again, we're going to build this with a few points. If we calculated all of these points, we'd be here for a lifetime, all right? These calculations are really a pain in the neck. Here, when we have the weak acid being titrated by a strong base, in this case NaOH, we again initially see this jump up as we move into the buffering region. We start off with just a weak acid, so the pH is low. We then jump up into the buffering region and we see this little spike up. We notice here the equivalence point is higher than 7. Why? Because when we titrate the all of the weak acid, we have all conjugate base in solution, and conjugate base is going to have a pH higher than 7. Then we again see this leveling off because we're essentially adding strong base to strong base, and we get this leveling off effect, just like we got added strong acid to strong acid and saw this leveling off effect. So these are a little bit different than the strong acid, strong base titrations when we look in the opposite directions. First of all, the pH at the equivalence point is less than 7 for this one and higher than 7 for this one. All right. The other thing is we see this initial drop or this initial increase in pH as we move into a buffering solution. The other thing here is we can calculate the pKa of the weak acid by looking half the equivalence point. It's not shown on here, but if we go to half the equivalence point, pH is equal to pKa. Let's take a look at what we're actually going to do. Okay, so it says a 25 milliliters of a 0.185 molar ammonia solution is titrated with 0.125 molar HCl. So ammonia is a weak base. HCl is a strong acid. So we're doing a weak base with a strong acid. The pH is going to start high, okay? And it's going to move down as we add more acid. The Ka of ammonia is given and the pKa of ammonia is given, and we're going to need both of those to do these calculations. It says, what is the initial pH of the solution? So when we add 0 milliliters of HCl, what is the pH we start with? What is the pH when 10 milliliters of HCl is added? So 10, what is the pH? What is the pH at the equivalence point? So we need to find what the equivalence point is and what the pH is. What is the pH at 1/2 of the equivalence point? So at half of the equivalence point, we need to find what that volume is. By finding the equivalence point, it's easy to find half of the equivalence point, but we already know what the pH is going to be. The pH is going to be 9.25 because at half the equivalence point, pH equals pKa. And it says, what is the pH when 40 milliliters of HCl has been added? So we have a lot of points to figure out here, 5 points. But like I mentioned before, the math here is a little bit more challenging than for the previous example. So I'm just switching over to the camera here, and it says, what is the initial pH of the solution? And in the initial solution, if you recall, we have 0.185 molar NH3. And we're given the Ka and the pKa, and the Ka here is equal to 5.68 times 10 to the minus 10. I probably should have put these on the slide. It's just when I chopped up the question, I didn't rewrite the whole question every single time. So what's going on in this initial solution before any of the HCl is added? Well, before any of the HCl is added, what we have is we have NH3 interacting with water to form NH4 plus and OH minus. And this question is exactly the type of question that was in the previous chapter. All right, so what is the initial concentration of NH3? Well, we're told that the NH3 is 0.185 molar. So we have 0.185 molar as the initial concentration of NH3. At the beginning of the reaction, there's none of this and none of this, so these are both 0. What about the change in concentration? Well, we don't know. We're going to gain X of this, and we're going to gain X of this. In order to make these things, we need to use NH3, so we need to lose X of this. So here we're going to get 0.85 minus X, X, and X. But if you notice here, we don't need a Ka expression because NH3 is not a strong acid, or weak acid, excuse me. NH3 is a weak base, so we need a Kb expression. So Kb equals concentration NH4 plus, concentration OH minus, divided by concentration NH3, like so. All right. Now we need a KB in order to plug in here, and then we can put our x squared and our 0.185. We're going to ignore the x like we have in the past. Well, how am I going to find KB? Well, KB equals KW divided by KA, or KA times KB equals KW, same thing. So we're going to take our 1 times 10 to the minus 14, and we're going to divide by our 5.68 times 10 to the minus 10. And when we do that, we find that KB is equal to 1.76 times 10 to the minus 5. Now we can plug in. 1.76 times 10 to the minus 5 equals x times x divided by 0.185, and as I just mentioned, we're going to ignore this x just like we did before. We cross multiply and we take the square root, and we find that x is equal to 1.80 times 10 to the minus 3, which also equals the concentration of OH minus. So now we can find the POH. The POH equals the negative log of the concentration of OH minus, right? So this is X, which is the concentration of OH minus. So we need the negative log of 1.80 times 10 to the minus 3. And when we do all that work, we find that the POH is 2.74. The pH equals 14 minus the POH, which equals 14 minus 2.74, which is equal to 11.26. All right, so now we have found that the initial pH of the solution is 11.26. One thing that I want to point out about this is that the initial pH of the solution is quite a bit higher than the pKa. If you remember from the buffering section, we said an effective buffer is plus or minus 1 from the pKa. So 10.25 to 8.25 as a pH range, or 8.25 to 10.25 if you prefer. And here, we're quite a bit higher than that, which means as we start to add acid and we start to make a buffer, you're going to see that initial drop off in the pH, which we talked about when we were showing when I showed the titration curve a few minutes ago. So in order to do this, we need to understand what's going on in solution. And before the HCl is added, we need to treat this simply as a weak base in solution. So we need to know to do this math, which is what makes this challenging, because it's not obvious that this is the way that we need to solve this problem. We have to think about how to solve the problem, and then we have to do all the math, which is a pain in the neck. But if we're not doing the right math, then we're going to end up getting stuck. So it's important to think about what's going on, just a weak base in solution, then do all the math, just like we did in the previous chapter. So for part B, we still have 25 milliliters of 0.185 molar ammonium, and we're titrating with the 0.125 molar HCl. But we want to know what the pH is when 10 milliliters of HCl is added. So in the previous section, when we looked at buffers, we added acids and bases to weak bases and acids without changing in volume. But in this case, we have a weak base and a strong acid, but we're adding milliliters, right? We added 25 milliliters and we added 10 milliliters, so there is a change in volume. Since there's a change in volume, if we want to find the initial concentrations of these things before they react together, so before the acid is added, we do need to use C1V1 equals C2V2. And this is a little strange because we say before acid, but we calculate the total concentration in the solution, so it doesn't quite exactly make sense, but I hope you get the idea. So if we get concentration of NH3, we want to use C1V1 equals C2V2. Well, the concentration of NH3 to begin with is 0.185 molar. The volume to begin with is 25.0 milliliters. The final concentration, C2, that's what I want to figure out. And the final volume is 25 plus 10, which is 35 milliliters. And when I do that, I find for NH2, C2 is equal, NH3, excuse me, C2 is equal to 0.132 molar. All right, so we've decreased the concentration from 0.185 to 0.132. So before the acid is added, this is 0.132 molar. How about for H+? Well, for the concentration of H+, I need to do the same thing. The H+ is 0.125 molar, and we're adding 10 milliliters of it. So again, C1V1 equals C2V2, but in this case, C1 is 0.125 molar, and the amount we add is 10.0 milliliters. C2 is still the variable, but this time V2, sorry, it's not the variable, it's still 25 plus 10, which is 35 milliliters. When we do that, we find that C2 here is 0.0357 molar. So 0.0357 molar. The initial concentration of NH4 plus we assume is 0. Now, does some of the NH3 react with the H2O to form NH4 plus? Sure, a little bit does, but because it's a weak acid, we're going to assume that that's negligible, and we're going to assume that this is 0. So if you notice here, in this reaction, which is one-to-one stoichiometry, we're going to have more acid than we have weak base, more base than we have strong acid. So said another way, we're going to lose all of our acid. We're going to lose some of our weak base, 0.0357 molar worth of it, and we're going to gain a little bit of NH4 plus, the same amount, 0.0357 molar of that. Notice that these numbers are all the same because we have one-to-one stoichiometry. Also notice we're losing reactants because these are going to react, and we're gaining products because we're going to form the product. So these are minus and these are plus. The other thing to notice is we subtracted out the total amount of H plus because there was less H plus. If there was more H plus, we'd have to actually subtract out the total amount of NH3, and that'll come up in a later problem. So after the addition, we're going to have 0 H plus. We're going to have this minus this, which is 0.0963 molar NH3. And we're going to have all of this, which is 0.0357 molar NH4 plus. Well, now we have a solution that contains both weak base and its conjugate acid. If we have that case, we can use the Henderson-Hasselbalch to find the pH. So pH equals pKa plus log base, which is NH3 in this case, over acid, which is NH4 plus in this case. So pH equals, I probably should have put the pKa again on this slide, but it was on the previous one. It's 9.25 plus log of 0.963, that should be a 0.0963, divided by 0.0357. And when I do that math, I find that the pH equals 9.68. So the pH went down quite a bit when we added 10 milliliters of acid, and this occurred because we moved into a buffered solution, and in a buffer solution, the pHs are relatively close to the pKa. The solution had an original pH of, I don't remember exactly, 11.5, something like that, and it dropped quite precipitously right at the beginning of the addition of acid because we're now moving into a buffered solution. Let's look at the next one. It says calculate the pH at the equivalence point, okay? And in this case, we need to do the same job that we did before, but we need to calculate the pH at the equivalence point, and in order to do that, we need to be able to find the volume of the solution at the equivalence point, because I need to know the concentrations of these different things. So in this case, the first job is to find the volume of HCl required to reach the equivalence point, because at the equivalence point, we are essentially going to have all NH4 plus, because you're going to have the same number of moles of H plus, the same number of moles of NH3, and you're going to make all NH4 plus. But in order to find the concentration of NH4 plus, you're going to need to know the total volume of the solution. So in order to do that, specifically to find the volume of HCl required for this, we're going to have to do a little bit of math. Specifically, we're going to have to convert from liters of NH3 to moles of NH3 to moles of HCl to liters of HCl. And you'll remember from the previous question, we know that we have 25 milliliters of 0.185 molar ammonia, and we're titrating with 0.125 molar HCl. So we're starting with the liters of this, which is 0.0250 liters of NH3. We now want to convert that to moles. In order to convert it to moles, for this particular NH3 solution, for every 1 liter, there are 0.185 moles of NH3. Said another way, it's 0.185 molar solution. Now we can convert this to moles of HCl using the balanced chemical equation. H plus is HCl. So 1 mole of HCl per 1 mole of NH3. And then we want to convert it to liters using the molarity of HCl. So for every 0.125 moles of HCl, there's 1 liter of this HCl solution. And when we do that, we find that it takes 37.0 milliliters of HCl to reach the equivalence point. I should have written this in liters, which is 0.0370 liters, which we can convert to milliliters of HCl. We now know the volume of the solution. We know that we started with 25 milliliters to begin with, and now we added 37 milliliters to that. Said another way, we have a total volume of 62.0 milliliters. We also know that all of the NH3 has become NH4 plus. So we can essentially use another dilution equation in order to figure that out, which is C1 V1 equals C2 V2. In this case, C1 is the initial concentration of NH3, because that's also going to be all converted into NH4 plus, which is 0.185 molar. The initial volume of NH3 that we used was 25.0 milliliters. The final concentration of NH3 is C2, but remember all the NH3 is going to become NH4 plus. And the final volume, which is why we had to do all this work, is 62.0 milliliters. And when we do all that math, we find that the concentration of NH4 plus, all conjugate base in solution, is equal to 0.0746 molar. So, to review what we've done so far, the first thing we did was we figured out how much HCl we had to use to reach the equivalence point by doing stoichiometry. Once we figured out how much HCl we had to use, we added that volume to the volume of NH3 that we started with to find the total volume. Realizing that all the NH3 is converted into NH4 plus, we found the concentration of NH4 plus using the dilution equation. There are, of course, other ways to do this. Now, we need to think about what's going on in the solution. What we've got in the solution is all weak acid. So now to find the pH, we need to do this in a very similar way to the way we did part A. In this case, the initial concentration of NH4 plus is 0.0746 molar. The initial concentration of H0 plus and NH3 are both 0. We're going to lose X of this and gain X of each of these. At the end of the day, we're going to have 0.0746 minus X for the concentration of NH4 plus, X, and X for the concentration of H3O plus and NH3. Note here that we're going to ignore this x. We can now write the Ka expression, and this is a Ka expression because in solution at the equivalence point, we only have the conjugate weak acid. So Ka is going to be H3O plus NH3 over NH4 plus. The Ka, we know, it's given in the original problem, which is 5.68 times 10 to the minus 10 equals x times x divided by 0.0746. When we do all this math and we solve for x, we find that it equals 6.51 times 10 to the minus 6 molar. And this is also the concentration of H3O plus because X is the concentration of H3O plus. Now we can find the pH. pH equals negative log concentration of H3O plus. pH equals the negative log of 6.51 times 10 to the minus 6, and the pH equals 5.17. So at the equivalence point, the pH is 5.17. Why is the pH less than 7 at the equivalence point? The reason for that is that all of that you have in solution is the conjugate base of the weak acid NH3. So at the equivalence point, we have a weak acid in solution. This weak acid is going to have a pH less than 7. So we see the pH at the equivalence point is less than 7. I understand that this is a lot of math because you do have to figure out the total volume and then find the concentration based on that total volume. Then make an ice table that you can do. This question was basically in the last chapter. Lots of work. All right, one more, lots of work. On the plus side, there's an easy problem here. So it says, what is the pH at 1/2 of the equivalence point? Well, at half the equivalence point, pH equals pKa, which equals 9.25. If you remember from a second ago, the equivalence point is at 37 milliliters. So this is going to be at 18.5 milliliters. The pH should be 9.25 at half of the equivalence point. All right, so now we have the last point on this curve, and then just one other mathematical operation we can do in these titrations, which is finding molar mass. It says a 25 milliliter, it's written wrong, 25 milliliters of a 0.185 molar NH3 solution is titrated with 0.125 molar HCl. What is the pH when 40 milliliters of HCl has been added? This is very similar to part C that we already did. Part B that we already did, except we've added a different amount of HCl. So the first thing I want to do is I want to realize that H plus is going to react with NH3 to form NH4 plus. In this case, I need to figure out the concentration of this and the concentration of this because there is a change in volume. So to find the concentration of NH3, I'm going to use C1 V1 equals C2 V2. All right. So I had 25 milliliters and the initial concentration is 0.185 molar times our 25 milliliters equals C2, that's my variable, times V2, which is 25 plus 40, which is 65 milliliters. When I do that, I find that the concentration of NH3 is equal to 0.0711 molar. So I'm going to go ahead and plug that in here, 0.0711 molar. Now I want to find the concentration of HCl. I'm going to do the same thing. All right, C1 V1 equals C2 V2. In this case, C1 is 0.125 molar. The volume of this that I'm going to add is 40.0 milliliters, which equals C2, that's X, that's what I'm looking for, times the volume that I added, which again is 25 plus 40, which is 65.0 milliliters. When I do that math, I find that C2 is equal to 0.0769 molar. So before the initial concentration of this one is going to be 0.0769 molar. What's important to note here is that we actually have more acid than we have NH3. This should not be surprising. We just found that the equivalence point was 37 milliliters. We've added 40 milliliters, so 40 milliliters should be past the equivalence point by 3 milliliters. And you find we have more moles of H+. Before we start, we assume that NH4+ has no concentration. All right? So in this case, unlike in part B, we actually have more acid than we do have NH3. So here we're going to lose all of our NH3. Again, since this is 1-to-1, we're going to lose all, or the same amount, of H+. We're going to gain the same amount of NH4+. What's this going to leave us with? Well, it's going to leave us with 0.00582 molar H3O+, 0 molar NH3, and 0.0711 molar NH4+. In this case, we have a strong acid mixed with a weak acid. When you have a strong acid and a weak acid mixed together, the pH is going to be much more affected by the strong acid, which completely ionizes, than the weak acid, which only ionizes to a very small degree. Said another way, this will have a great effect on the concentration of H3O+. This will only have a minor effect on the concentration of H3O+. So the pH is based on this. Well, this is the H3O+ concentration. So the pH equals the negative log of the concentration of H3O+, and this is the concentration of H3O+. So it equals the negative log of 0.00582, which equals 2.23. Okay? So, ton of work in order to solve these problems. You need to not only understand which equations to use, but you need to understand what's going on in the solution, what species is there, what happens when you have more H+, what happens when you have less H+, what happens when you just have conjugate base, or conjugate acid, what happens when you just have base. There's a lot going on here, and this stuff absolutely takes practice. Let's look back to our slide. And our slide says, our slide gives us the answers to each of these questions. So we found that the initial pH is 11.26. Said another way, when we add 0 milliliters of HCl, the pH is 11.26. When we add 10 milliliters, the pH quickly drops to 9.68 as we get into a buffering region. So we see this initial drop off in pH. At half of the equivalence point, which is 18.5 milliliters, because we calculated the equivalence point and then just divided it by 2, we find that the pH is 9.25, which is the same as the pKa. So at 18.5 milliliters, the pH is 9.25. At the equivalence point, which is a volume of 37 milliliters, we solve for a pH of 5.17, which, as we talked about, is less than 7 because what was in solution was NH4+, which is a weak acid. So we had a weak acid in solution, so therefore we had a pH of less than 7. Finally, when we added 40 milliliters, we started to come down here to a point where we now have acid solution, and we're adding more acid solution to acid solution, so it's just going to slowly come off. This pH is just going to slowly drop until it reaches a point where it will not drop anymore. So this is the titration of a weak base with a strong acid. Just by way of review, I want to point one more thing out about this. Same thing I pointed out before. If we have a weak base being titrated with a strong acid, we see an initial drop off in the pH as we move into the buffering region. In here, we have the buffering region. If we find the equivalence point at half of the equivalence point, pH equals pKa, because in the Henderson-Hasselbalch equation, log base over acid, base and acid are equal, and when base and acid are equal, the pH equals the pKa. We also found that the pH is less than 7 for this titration at the equivalence point. Why? Because we have the conjugate acid in solution. And then as we fall off, the pH behaves very much like a strong acid, strong base at the bottom because we're just adding acid to acid solution, just like in the other titration. What about the opposite of this? Well, in the opposite case, where we have a weak acid, we start with a low pH and we quickly go up as we move into the buffering region. The pH of the equivalence point here is higher than 7 because we have conjugate base in solution. As we get past that, we again flatten off because we're adding strong base to strong base, essentially. Okay, so this is the titrations of weak bases with strong acids and the titration of weak acids with strong bases. This is not easy, and it definitely takes practice. The last thing that we can calculate is what is the molar mass of an unknown monoprotic acid if a 0.2834 gram sample is titrated to the equivalence point with 28.23 milliliters of 0.1009 molar NaOH solution. Okay, so if I could switch back here to my camera, we can go ahead and solve this one. So in this case, I've given the mass and I'm given some information about a titration. So what we want to remember is that the molar mass equals grams divided by moles. In this case, the grams are given here, okay? And the moles we can figure out from this information. Specifically, what we want to do is we want to use the NaOH solution information, because we titrated it to the equivalence point, in order to find those moles. Very specifically, we want to take liters of NaOH and convert it to moles of NaOH, and then finally to moles of HA. We have grams of HA. If we put in moles of HA, we will have molar mass. So, starting here with this in liters, 0.02823 liters times, well, now we need to convert this to moles, which is going to be, for every 1 liter of NaOH, this particular NaOH solution contains 0.1009 moles of NaOH. Times, now we want to convert from moles of NaOH to moles of HA. Well, they have a 1-to-1 stoichiometry. So for every 1 mole of NaOH, there's 1 mole of HA. And when we do all that math, we find that there are 0.002848 moles of HA. Now we can plug this into this molar mass expression. So the molar mass equals the grams, which is 0.2834 grams, divided by the moles, 0.002848 moles, which is going to be equal to 99.49 grams per mole. So this last titration question essentially could have been asked in the General Chemistry 1 section on stoichiometry, but it doesn't really fit in anywhere because it's not based on the titration curves. But there's a lot to titration, so it's going to be really important to practice with this.